In this video, we'll be talking about graph transformations. So before we begin with that, let's remind ourselves about some of the basic functions that we'll be talking about in this class and what their graphs look like. So each of the graphs that you see on the screen, often we refer to them as the parent graphs, because these are untransformed basic functions that we want to know how to sketch. So the first one in the top left corner is the constant function, f of x equals c, where c is any real number. And that's just going to be a horizontal line at the height c. So in this case, the c is somewhere between 1 and 2, but you could draw this for any real number c. So if it was f of x equal to -1, that would be the horizontal line here at -1, etc. So we want to know the constant function, and its domain is all real numbers, and it's constant on the entire interval. The next type of function that we want to know how to sketch is f of x equal to x. This is just a straight line of positive slope 1, and we'll learn more about lines and be able to draw a variety of lines, but in particular, we want to know that the function f of x equals x, or y equals x, is this diagonal line that passes through the origin. It also has domain all real numbers and range all real numbers, and any point on this line is going to have coordinates. So for example, this point is 1, 1, or this point is -1, 1. So on the line y equals x, all of the points have this property that the x and y coordinates are equal. Next, we'll like to know the absolute value function, and we've already seen this function in our previous videos. It's this v-shaped function resting at the origin. This is y equals absolute value of x. So in this case, we still have all real numbers as our domain, but you can see that the range now is from 0 to infinity, because the absolute value function always gives you a positive output. And we should be able to determine on which interval the function is decreasing. It looks like that's from -infinity to 0. On which interval the function is increasing, that's from 0 to infinity. Then the other thing you'll see written here is that this is what's called an even function. We have functions that are called even, some functions are called odd. We're going to learn about this concept in our next video. So for now, you don't have to understand even or odd, but in the future we will learn that, and then you can add that to your understanding of these basic graphs. Next, the standard quadratic function is f of x equal to x squared. This is a shape called a parabola. It has domain all real numbers and range 0 to infinity. Just like the absolute value function, it's decreasing from -infinity to 0, increasing from 0 to infinity, and it is even. We also need to know the graph of square root of x. That's pictured here. We have domain and range from 0 to infinity, and it's an increasing function. The standard cubic function x cubed has this snake shape. Its domain is all real numbers, range is all real numbers, and it's an increasing function everywhere. And similarly, the cube root, x to the power 1/3, or cube root of x, has also this kind of S shape, and its domain and range are all real numbers, and it's increasing everywhere. These are both odd functions. So we should know how to sketch these functions. They don't have to be beautiful drawings, but just roughly approximate sketches. And we're going to be using them for the rest of this lecture. So that's why we wanted to review them really quick before we got started. So as I said, this lecture is about transformations of functions and transformations of graphs of functions. So this table here is something that you're going to want to keep handy and refer to, because it tells you each of your transformations. We have several different types, and how those affect the domain, the range, and the graph of the function. So The first type of transformation would be a vertical shift. Whenever we're doing any transformation of a function, the first question we're going to ask ourselves is if the transformation is affecting the x-coordinate or the y-coordinate. So if we're talking about a vertical shift, does it seem like that should be changing the x-coordinates or the y-coordinates? Well, it's actually going to be changing the y-coordinates, and that makes sense because the y-axis is our vertical axis, so a vertical shift is affecting our y-coordinate. And how will we recognize it? Well, you'd have something like y is equal to f of x plus some constant c, or y is equal to f of x minus some constant c. And here in the rightmost column, you can see the change that is affected is that if you have f of x plus c, c is added to f of x. If you have f of x minus c, c is subtracted from f of x. And we know that f of x is our y-coordinate, so we're either adding c to the y-coordinate or subtracting c from the y-coordinate. And the effect of this on the graph is going to be to raise the graph by c units if we're adding c, or to lower the graph by c units if we're subtracting c. And of course, we're going to work through lots of examples and see pictures of these graphs, so we'll understand what's happening as we work through the examples. The next type of transformation would be, rather than a vertical shift, a horizontal shift. And we know that the vertical shift is affecting our y-coordinate, so it makes sense that the horizontal shift will be affecting our x-coordinate. And what will this look like? How will we recognize it? Well, now you can see we're still adding or subtracting c, but this adding or subtracting c is taking place inside of the function f of x, or it is with the x-coordinate. Now there's a little bit of a twist here, because the change that happens when we add c is that we shift the graph to the left by c units. If we subtract c, we shift the graph to the right by c units. And that's because in our equation, we're replacing x by x plus c, or x by x minus c, respectively. And this has perhaps a counterintuitive effect. So the vertical shifts were very intuitive. If we added c, that meant we were going up. But in the case of the changes that we make with our x-coordinate, this has sort of the opposite result. We are adding c, that means we shift to the left, or in the what we typically think of as the negative direction. If we subtract c, then we shift to the right, which is typically what we think of as the positive direction. So we want to remember changes to our y-coordinate are intuitive, changes to our x-coordinate are counterintuitive. The next type of transformation we might see is a reflection across the x-axis. So let's imagine I have my coordinate axis and I have a point sitting somewhere. If I reflect that point across the x-axis, now it's down here, which coordinate did I change? The x-coordinate or the y-coordinate? Well, I changed the y-coordinate. The location of the x didn't change, but I switched from positive to negative. Or if I thought about reflecting it back upward, that would be switching the y-coordinate from negative to positive. So we want to remember that a reflection across the x-axis is actually affecting our y-coordinate. How is it affecting it? Well, our y-coordinate is multiplied by -1, or it just changes signs. We could also have a reflection across the y-axis. So again, let's think about our coordinate axes. Here's y, here's x. And say I have some point. If I reflect it across the y-axis, now it's over here. So I'd ask the same question. Was my x-coordinate affected or my y-coordinate affected? Well, the y-coordinate didn't change because I still am at the same height. but the x-coordinate changed from positive to negative. So how will I recognize this transformation algebraically? This is going to be f of negative x, where we replace x in the function by negative x. Okay, so those are reflections. What else do we have? Well, we also have vertical stretching or shrinking and horizontal stretching or shrinking. So vertical stretching or shrinking, by now we understand this is going to be a change to our y-coordinate. And how will we recognize it? Well, algebraically it's going to look like some real number c multiplied with the y-coordinate, or multiplied with the entire function. If the c is greater than 1, then that's going to be vertical stretch. If the c is between 0 and 1, so it's some fraction or decimal like 1/2 or 1/4 or 2/3, then that's going to be vertical shrink. So that, again, is pretty intuitive. If we have a number larger than 1 and we multiply all of the y-coordinates of the function by that multiple, the function gets stretched vertically, whereas if we have a number between 0 and 1 and we multiply, the function gets shrunk vertically. But we may also have horizontal stretching or shrinking, and this will be multiplying a real number c inside the function, or with the x-coordinate, as you'll see here, f of c times x. And as we saw before, the changes to the x-coordinate are somewhat counterintuitive in the sense that now if we have a c larger than 1, this results in a horizontal shrink, whereas if we have a c between 0 and 1, this results in a horizontal stretch. So this is the table of the transformations, and we're going to start working through examples. As I said, let's keep this table handy to refer back to. We'll work through these examples and see if we can understand these transformations a little bit more. Our first example asks us to use the graph of y equal to f of x, as pictured here, to find the graph of g of x equal to negative f of x. So negative f of x is a transformation of the graph. The first question, as always, that I want to ask myself is, am I transforming the x-coordinate or the y-coordinate? So this appears to be transforming the y-coordinate because I have a number multiplied with f of x, which is the y-coordinate, and because the number is -1, I know that this is reflection across the x-axis. And reflection across the x-axis does change the y-coordinates. So for example, if I pick any point, like maybe this one here, its reflection across the x-axis is going to be the same x-coordinate, but the positive version of the y-coordinate. So this point's going to end up here, this point here, here. Let's use a different color. So here's the reflection of that point. This point that's located at -2 and 4 would become -2 and -4. And so the reflected graph would look like the green graph that I've drawn. So we just need to look at the choices below and determine which of them is correct. And it looks like the picture that we found is pretty similar to A. So A is going to be the transformed graph, which is the reflection across the x-axis. So this is where, as I say, we're going to need to keep our table handy because we're constantly going to need to refer to what each of these is. Example 2, again, use the graph of y equal to f of x to graph g of x equal to f of x plus 1. So this graph is f of x. I want to transform the graph. So it looks like I have a number added inside the function or added to the x coordinate. So that's going to transform the x coordinate. I also have a number added outside the function or to the y coordinate. So that's going to transform the y coordinate. So this one is going to be y coordinate transformation. And what kind of transformations are they? Well, in both cases, I have addition. And I know that addition is shifting. Addition or subtraction just gives us shifting. So I'm going to have the x coordinate shifted by 1. I have to figure out, am I going to the left or to the right? And I'm going to have the y coordinate shifted by 4. I have to determine, am I going up or down? So I know that the y coordinate transformation is intuitive. So if it's plus 4, that's shift up by 4. And the x coordinate transformation is a little bit counterintuitive. So if it's plus 1, that means I actually want to move in the negative direction, which is left, by 1. So I can recognize that I want to take each point and I want to shift it left by 1 and up by 4. So for example, this point, the rightmost point on the graph, if I shifted it left by 1 and up by 4, it should end up here. And I could do the same thing with each point. This point, left by 1 and up by 4, would end up here, and so on. So I'm going to look down at the options that I have and try to determine which of them is correct. I know these graphs are kind of small, but this should be, again, it should be A, the correct graph, because I knew that it was shifted up by 4. That would help me narrow it down to between A and D. And then if I look at A is shifted to the left by 1. If I look at D is shifted to the right by 1. So I wanted to choose A for this example based on what we discussed above. Okay, let's see another example. Graph the standard quadratic function x squared, then use transformations of this graph to determine the graph of g of x equal to x minus 4 squared. So we're going to remember, I'm just going to, very small off to the side here, draw our coordinate axes and remember that our parent graph of x squared looks like a parabola that's sitting on the origin. So this is the parent graph x squared. The transformed graph, g of x, is x minus 4 squared. So this transformation, because the 4 is subtracted from the x coordinate, this is going to be a shift, and I just have to determine shift left or shift right, because I know that it's affecting the x coordinate. So this shift, because it's negative 4, should actually be shifting in the positive direction, or right, by 4 units. Okay, so I know that I want to take my parent graph and shift it right by 4 units, and I just look at my options here and see which one of these looks right. So I can eliminate C and D because C is shifted up and D is shifted down. So it should be between A and B. Which of the graphs is shifted right by 4 units? Well, it looks like that would be the graph B. All right, so that's my correct choice for that exercise. Now, example 4, graph the square root function, f of x equals to square root of x, Then use transformations to determine the graph of g of x equal to square root of x plus 1, where this plus 1 is added to the y coordinate because it's taking place outside of the square root. So again, we'll remember our parent graph. And this is why I say it's so important to know these guys, and we don't have to draw them perfectly, just quick sketches. So in our parent graph, square root of x, we have domain and range 0 to infinity. We start at the origin, and it looks roughly like that. And we know that the point 0, 0 should be on the graph, 1, 1 should be on the graph, and 4, 2 should be on the graph. Okay, so if I want to take this graph square root of x and add 1 to the y coordinate, that should be shift up by 1 unit. So shift up by 1. Then let's look at our choices of graphs and try to determine which of them is shifted up by 1. Well, if I look at A, that appears to be shifted to the right by 1. B is maybe shifted left by 1 and down by 1, but it's definitely not shifted up. D is shifted left by 1, and C is the only one that is shifted up by 1. So because we had square root of x and the plus 1 was outside, this should be our correct choice of graphs. What if we have the same parent graph, square root of x, but now we're told that the transformation is minus square root of x plus 2? Well, now I see I've got a couple of things going on here. I've got negative multiplying the function, so I know that that's reflection across the x-axis. What else do I have? I also have addition under the square root, or inside the function, or with the x-coordinate. So reflection across the x-axis, that's a transformation of our y-coordinates. And we have shifting of the x-coordinate. Do I go left or do I go right? Well, it's plus 2, so I know that means I should go left by 2. And we know what our parent graph looks like. So which of these graphs is shifted left by 2 and reflected across the x-axis? Well, all of them have the reflection, you can see, because the basic shape that we started with was this one, and they're all reflected across the x-axis. So then we just determine which one is shifted left by 2 units. And that looks like it should be B. All right, very good. Example 6, we start with the parent graph, absolute value of x. And the transformation, g of x, is absolute value of x, and outside of the absolute value, plus 4. So this is affecting our y-coordinate. So we know that it's going to be, because addition, it's going to be shift up or down. And which one do we choose? Well, positive 4 is shifting up by 4 because the transformations of the y-coordinate are intuitive. We know that the graph of absolute value of x has this V shape and it sits on the origin. So we're looking for a V-shaped graph that is symmetric around the y-axis but just moved up by 4 units. That should be graph A. So let's see another example where we have 2 transformations taking place simultaneously. Again, the same parent graph, square root of x, but now we have 2 times the square root of x plus 2. The 2 is added inside the absolute value, so the 2 is added to the x-coordinate. That's a transformation of the x-coordinate. And this other 2, the 2 that's multiplied, it's multiplied outside of the absolute value, so it's being multiplied with the y-coordinate. So we have one transformation to the x-coordinate and one transformation to the y-coordinate. We want to figure out how these transformations are going to affect our graph. Let's first address the x-coordinate. So that's the x plus 2 inside the absolute value. So we know that this is a horizontal shift. Do I go left or do I go right? Horizontal shifts are counterintuitive, so we're going to go left 2 units. Now I have a multiplication of the y-coordinate, so that's either vertical stretching or vertical shrinking. And I have to choose between stretching and shrinking. I know that transformations of the y-coordinate are intuitive, so since I'm multiplying it by 2, that should be vertical stretch by a factor of 2. Okay, so these are my two transformations, shift left by 2, vertical stretch by 2, and I have to choose which of the graphs has those properties. So first of all, if I call these A, B, C, and D, then A and B are the two graphs that are shifted to the left. So we can rule out C and D and just try to choose between A and B. And vertical stretching by 2 means that my graph is going to get taller and thinner. So it's going to be this graph B. So the vertical stretch is going to make the graph, instead of its usual V shape, it's going to, each of the y-coordinates is multiplied by 2, so if this y-coordinate is multiplied by 2, then it moves all the way up to here. So it's taller and skinnier. So B is going to be our correct graph for the transformation g of x. All right, let's see one more example of this type. We want to start with the parent graph x cubed, and we know that the parent graph x cubed looks like this. That's the rough shape, kind of an S-shaped thing. So first of all, A doesn't even have the right parent graph. So I can eliminate A as a possibility and just focus on B, C, and D. What kind of a transformation do I have here? Well, I have the number 1/3 multiplied with the y-coordinate, or outside of the function. So I want to point out the difference here between if I had a horizontal stretch, then this 1/3 would be inside the parentheses. Since I have a vertical transformation, the 1/3 is outside, so I could think of this as having parentheses here around x. Okay, so when we don't see any parentheses, we interpret this as the 1/3 is not being cubed. It's outside on its own, so that's a transformation of the y-coordinate. So it's vertical stretch or vertical shrink, and I have to determine which one. Since transformations of the y-coordinate are intuitive, and this is a number between 0 and 1, should be getting smaller. So this should be vertical shrink by a factor of 3. Okay, then I look at my parent graph. What does it mean, vertical shrink? Well, that means I should be getting shorter and kind of wider. Still maintaining the S shape, but becoming shorter and wider. So if I look at D, D looks like a vertical stretch. It's getting taller faster. And if I look at C, C has this reflection, which we don't have. So I can eliminate C and D, and that means B should be my correct graph. For vertical shrink by a factor of 3, my graph is a little bit stretched out. Okay. So let's do a different type of exercise now. Example 9, we have this graph pictured here on the right, and we're told to write an equation for the function whose graph is shown to the right. And it tells us this is a transformation of a common function. We know this. The parent function, in this case, we should be able to say right away, is square root of x. So we know that this is going to be some transformation of square root of x. So some combination of adding or subtracting numbers to the x and y coordinates, or multiplying numbers to the x and y coordinates, or reflecting the x and y coordinates by multiplying by -1. So these axes here, these are units of 1. That's what this information at the bottom means. So this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So just so that we have the scale right. So we know that the parent function square root of x does start here at the origin, and it would have the point 1, 1, and it would have the point 4, 2, and it would have 16 and 4, which is a little bit out of our scope, but it would essentially look like this. That would be the basic graph, square root of x. This graph looks very similar to that, but it is shifted to the right by 4. So if we wanted to describe this picture, it would be square root of x, then shifted right by 4. So we have to figure out how to express that as a transformation. So to express this, we know that we're either going to add or subtract 4 to the x coordinate, and the transformations of the x coordinate are counterintuitive. So if I want to move in the positive direction by 4, I need to subtract 4. So g of x equal to square root of x minus 4, and this subtraction is taking place under the square root, or with the x coordinate. That will be the graph of f of square root of x shifted right by 4. So this should go in this box here. Okay. Now we have, for each of the following graph transformations, give the x and y coordinates of the point on the graph, which corresponds to the point -1, 1 on the original graph. Okay, so we don't have a scale here, but I think probably it's pretty safe to assume that this is -1, -1. Or actually, I think that's what, yeah, this is. So this point, -1, -1. So here's the point P, -1, -1. And we're going to transform this graph in a few different ways and see how does this affect the point P? So the first transformation, shift the graph up by 10. So just to kind of sketch that out, we don't have the appropriate scale, but let's say this was shift up by 10. Then here's my graph. So what happened to this point P? Did the x-coordinate change or did the y-coordinate change? Clearly just the y-coordinate has changed. So we are going to add 10 to the y-coordinate, and that's evident from the picture. The x-coordinate is still -1. The y-coordinate is -1 plus 10, which is 9. Then we're asked to stretch horizontally by 6. So we know that horizontal stretch is affecting our x-coordinate, and because it's stretch or shrink, it's multiplying the x-coordinate. I'm going to leave a little room there because I'm going to fill in. What do I want to multiply with the x-coordinate? Well, again, we know that transformations of the x-coordinate or of the horizontal coordinate are a little bit counterintuitive. So stretch means to make something bigger. We would think that that would be a number bigger than 1. So since it's counterintuitive, that should be a number less than 1. So we're looking for a number between 0 and 1 that would result in stretching horizontally by 6. Well, that should be 1/6. So I want to multiply 1/6 with the x-coordinate. That's going to be -1/6 and -1. Okay. And flip vertically is our final transformation. So to flip this graph vertically, we would see that it should get this shape now. So what happens to this point, -1, 1? Now it's here. And again, I would ask myself, did the x-coordinate change or did the y-coordinate change? Clearly, only the y-coordinate changed. And how did it change? Well, it just changed signs. It went from being -1 to +1. So the point is now -1, +1, because we multiplied the y-coordinate by -1, or we just changed the sign. Of the y-coordinates. That's the same thing as saying we multiplied the y-coordinates by -1. And you can see, if we go back and look at the sketch that we drew, where the y-coordinates were positive, now they became negative, and wherever the y-coordinates were already negative, now they became positive. So we literally just switched the signs. Okay. Now, we're given a picture and we're told that this is the graph of y equals x cubed minus 6x squared. And then the graph to the right is some transformation of y equals x cubed minus 6x squared. We want to find a formula for the transformation. So I find that it's probably best to focus on certain points, which is why, as you can see, they've given you the coordinates for certain points. This one isn't given, but we can see that it's 0, 0. Now, another thing that I want to do is I want to notice the shape of the graph on the right. It looks like a reflection across the x-axis of the graph on the left. So now this relative minimum, it looks like it's become a relative maximum. This relative maximum has become a relative minimum. So let me use colors to coordinate. So the relative maximum became relative minimum and vice versa. So that tells me, first of all, it looks like I have reflection across the x-axis. I'm just getting that from looking at the shape. Then I want to think about how the coordinates change to see whether I have vertical or horizontal shifting. The point 0, 0 was transformed to the point 0, -8. So the x-coordinate didn't change, it's still 0, but the y-coordinate changed to -8. The point 4, -32 becomes 4 and 24. So again, the x-coordinate clearly didn't change, but the y-coordinate changed. So we're going to have a vertical shift, pardon me. And it seems like that vertical shift involves the number 8. We just have to figure out if it's up or down. So let's see. I'm going to use this space here. So we'll remember what our original graph looks like. And let's just sketch what it would look like if we shifted it or if we reflected it first across the x-axis. So I would have still the point 0, 0, but now coming down to 0, 0, and then going up to this hump and then back down. So the point 4, -32 now is 4 and 32. And the point 0, 0 is still 0, 0. So that's the reflection across the x-axis. Now if I look at the final product that I want 4 and 24, 0 and -8. So that is exactly shifting down by 8 units, or subtracting 8 from the y-coordinate in both cases. So I'm going to just put here a down arrow to say vertical shift down by 8 units. Now our function is x cubed minus 6x squared. So if I first do reflection across the x-axis, then that's going to give us negative of x cubed minus 6x squared. And then vertical shift down by 8 units is going to result in minus x cubed minus 6x squared minus 8. Or if I want to distribute this negative, I can write it as minus x cubed plus 6x squared and minus 8. So if I call this graph g of x, then g of x is equal to minus x cubed plus 6x squared minus 8. Could I have also done those transformations in a different order? Let's see. So let's think about, instead of taking care of the reflection first, let's take care of the shift first. If that were the case, then first I would need to shift up. So my graph looks like this. So this point 0, 0 would become 0 and positive 8. And the point 4 and negative 32 would become 4 and negative 24. That would be, so first I could shift up by 8. Then, if I do the reflection, 0 and 8 becomes 0 and negative 8. 4 and negative 24 becomes 4 and positive 24. And this will be my shape. So either way, I end up with the same graph in the end. If I were to first shift by negative 8, then first shift up by 8, then x cubed minus 6x squared would become x cubed minus 6x squared plus 8. Then when I do the reflection, I put the parentheses around everything and say that it's negative. So then g of x would be negative x cubed plus 6x squared minus 8. Well, that's exactly what I found before. So the reason I did this is just to show you that as long as we are careful, we can usually do this in either order. It's not going to make a difference, but you can see that depending on whether I reflected first or second, this vertical shift was either shifting up by 8 or shifting down by 8. So it does depend which order you do it in, and that's why you need to be a little careful, but as long as you're careful, you should get the same result. Okay, let's do one last example here. Again, we have a graph. We're going to call this function f of x, and we want to match this given list of transformations to the choices shown below. So we'll have a list of transformations, and these are the graphs we're going to choose amongst. So first, let's look at our list and see if we can determine what kind of transformations we have. So the first is f of x minus 2. And we're not even thinking about what the function f looks like at this point. Just in general, what kind of a transformation is f of x minus 2? Well, I see that I have 2 subtracted from the x-coordinate, so this should be a horizontal shift. Should it be left or should it be right? Because horizontal shifts are counterintuitive, it should be shift right by 2. What about number 2? We have f of 1/2 x, so I have a number multiplied with my x-coordinate. So I know that this should be horizontal stretch or horizontal shrink. And which one do I choose? Well, a number between 0 and 1, like 1/2, is going to give me a horizontal stretch by a factor of 2. And then what if I have subtraction outside the function or subtraction from the y-coordinate? I know that that's vertical shift, but do I shift up or do I shift down? I'm going to shift down by 2 because the vertical transformations are more intuitive. In number 4, I have 2 transformations. I have vertical stretch or shrink because I have a number multiplied with my y-coordinate, and I have horizontal shift because I have a number subtracted from my x-coordinate. So I have vertical shrink by 2 because vertical transformations are intuitive, so a number between 0 and 1 means I shrink by 2. And I have horizontal shift. Rather, I'm going to say shift to the left or to the right. In this case, I choose to the right because it's subtraction, and that's counterintuitive. Shift right by 1. Okay. Number 5, y equal to 2 times f of x. This is vertical stretch because it's multiplied with the y coordinate, and that's intuitive. And finally, I have minus f of x plus 3. This is a lot like the last example we just did, where maybe it makes a difference which order we do this in. So this is going to be reflect across the x-axis because I see that my y coordinate is multiplied by -1, and then shift vertically up by 3. So writing these descriptions is going to help us to identify the correct graph. So let's say f of x minus 2, the first one, we know that that's shifting right by 2. Let's take one more look at our graph and see if we can pick out which graph below is shifted right by 2. So the y coordinates are not changing, just the x coordinates are moving right by 2. Well, that looks like it should be graph A. This is f of x minus 2, because our original graph was exactly this graph, except just moved over 2 units everywhere. So this was our original graph, over 2, over 2. So that graph, the black graph is f of x minus 2. The red graph I just sketched in was our original f of x. Okay. What about, so this one's A. What about horizontal stretch by 2, which is f of 1/2 x? So again, I know that my y coordinates aren't affected. So if I look at this red sketch that I made of f of x, the y coordinates should stay the same. What is affected? I have horizontal stretch by 2. So graph B looks like it might have some stretching or shrinking. Graph B looks like it has some stretching or shrinking, but I also see that the y coordinates are affected, so that seems like it shouldn't be right. Similarly, graph, let's call this D, E, and F. D has some stretching or shrinking, but the y coordinates have changed, so that can't be right. So I'm going to say that F should be correct for horizontal stretch by a factor of 2, because the y coordinates have not changed, but you can see that the graph is much wider horizontally. So f of 1/2 x is going to be F. How about shifting down by 2? So in this case, my x coordinates are not changing at all. The only thing that's changing is that my y coordinates will be shifting down by 2. That looks like that should be exactly graph C, because I can see I still maintain exactly the same shape as my original graph, and what has changed? Everything is just shifted down by 2. So this is C. And vertical shrink by 2 with shift right by 1, that's number 4. Let's take a look. Vertical shrink by 2, shift right by 1. Well, clearly D is not a vertical shrink because the graph has gotten much taller. And E, one thing I noticed about E is that it has this reflection. So that's not my correct graph. So I believe it should be B. So 1/2 f of x minus 1 is B, and we can see the shifting left by 1. This was at -4 and 0, now it's at -3 and 0, and the height, where this maximum height used to be 4, now it's 2. So it's exactly 1/2 f of x minus 1, vertical shrink by 2, shift right by 1. So that's B. Vertical stretch by 2, that must be D, because clearly D is stretched, but otherwise the x coordinates have not changed, just the y coordinates are doubled. So that's D. So that means finally that the only graph that's left should be E. Reflect across the y-axis and shift up by 3. We can take a look at E and see that that does look like exactly what happened, because this point used to be here at 0, 4, so it got reflected down to 0, -4, and then shifted up by 3. And you could do that with each of the points and see that that is in fact the graph that has been reflected and then shifted up by 3. Okay, so that completes that exercise, and we'll go ahead and finish the video here, and we'll learn more in our next video.